Lawrence Livermore National Laboratory has developed the world's most laser damage-resistant fused silica optic used at ultraviolet wavelengths for high-power laser systems. Most laser systems need accurate diagnostic optics to measure the power and energy being delivered to the target. Because these optics are typically at the output of the laser system where the beam is at its peak fluence, they are frequently damaged and need to be replaced regularly. The laser damage-resistant, anti-reflection grating debris shield, or AR-GDS, is a 43 by 43 centimeter transmissive optic with an optical diffraction grating imprinted on its surface. This grating redirects a small fraction of the main beam to a diagnostic package used to measure the energy of the laser. LLNL developed the AR-GDS to handle the particularly destructive environment of world-class fusion systems such as the National Ignition Facility, or NIF. Compared to its predecessor, the standard GDS, this optic reduces the rate of damage by a factor of 20, while increasing the transmission of light to the target by 4%, ensuring that the system remains economical while operating at a higher power and energy. Prior to the AR-GDS, standard GDSs were used with an uncoated grating, since AR coatings at the time were not environmentally stable enough for accurate grating operation, or they could not survive the high fluence UV laser light. A standard GDS was disposed of after approximately 6 months of use due to the large amount of laser damage on the optic. This laser-induced damage came from two sources: near atomic scale absorbers left on the optic from the surface finishing and grating imprint processes, and laser-generated debris originating from intense reflected diffracted orders of light striking hardware near the surface of the optic. There are three major technologies developed at Lawrence Livermore National Laboratory that enable the improved performance of the AR-GDS. The first technology is a patented chemical etch process called the Advanced Mitigation Process, or AMP. AMP eliminates near atomic scale absorbers, which can act as precursors to laser damage. This process dramatically increases the inherent damage resistance of fused silica optics. The second technology is a novel anti-reflection coating that is both highly damage resistant and environmentally stable. The coating is comprised of 20 nanometer porous silica colloids manufactured using sol-gel chemistry. The coating is treated with hexamethyl disilazane, making the coating both hydrophobic and more resistant to absorption of volatiles, such as plasticizers, and thus environmentally stable. Finally, the third technology is an improved photolithographic grating manufacturing process, which has been modified to accommodate the presence of the AR coating. This process implements off-axis exposure, gradient etching, and optimized etch depth to improve the uniformity and performance of the AR-coated grating. When AR-GDSs were deployed on NIF in 2016, the number of laser-initiated damage sites during 6 months of use dropped to 65 sites per optic, down from 1,300 sites per optic when standard GDSs were used. This dramatic reduction in damage allows the AR-GDS to be economically repaired and reused for more than 7 years, rather than being disposed of after 6 months of use. The AR-GDSs will ultimately reduce the operating costs associated with this optic by more than 600%, while at the same time deliver more power and energy to the target of fusion-class laser systems. As demand for power and energy for such laser systems increases, the AR-GDS can be scaled to support these applications with a stable diagnostic optic that delivers more power and energy to the target while operating at a fraction of the cost of other available technologies.